When do humans actually leave the solar system? If leaving means going past the planets, we already did that. If it means entering interstellar space, our probes already did that too. But if it means truly escaping the sun's outer reach, then humanity is not even close. Because now you're not asking when we build a better rocket, you're asking when human bodies, life support, power systems, autonomy, and entire closed environments become strong enough to survive where Earth can no longer save them. So where do most people put the edge? Usually at Pluto. That feels natural. Pluto's far away. It used to be called the 9th planet. And in a lot of people's minds it still feels like the last stop before deep space. But that is the first mistake. Pluto is not the edge of the solar system. It is part of the inner known structure compared with what comes after it. If your definition is just past the planets, then we crossed that line decades ago. Robotic missions went beyond the main planetary region a long time back. So if that is your standard, then the question is already over. But that answer feels wrong, and it feels wrong because you know the real question is bigger than that. You're not asking whether we got past some planets, you're asking whether we got out. And once you ask it that way, the next boundary appears. That boundary is the heliosphere, the huge bubble of charged particles created by the sun. When a spacecraft crosses the heliopause, it has moved out of that bubble and into interstellar space. That sounds final. It sounds like that should settle everything. Except it still does not. Voyager 1 crossed that boundary in 2012. Voyager 2 crossed it in 2018. That means human-made hardware has already entered interstellar space, so now you get a strange result. If someone says, have humans reached the space between stars? The honest answer is yes, through machines. But if someone says, have humans truly left the solar system? The honest answer can still be no, depending on the definition. That is not wordplay. That is the core of the whole topic. Crossing the heliopause means leaving the heliosphere. It does not automatically mean leaving the solar system in the wider gravitational sense. So now the obvious question gets worse. If leaving interstellar space is not enough, then what is enough? This is where the Oort Cloud changes everything. The Oort Cloud is a vast, distant shell of icy bodies thought to surround the solar system very far from the sun. And once you include it, the scale of the story changes immediately. Pluto is out at around a few dozen times the Earth-Sun distance. The inner Oort Cloud may begin thousands of times the Earth-Sun distance from the Sun. The outer Oort Cloud may extend tens of thousands of times further still. That is not a minor extension of the map. That is a completely different scale. This is the point where normal intuition stops helping you. Most people think the solar system is basically the sun, the planets, and maybe a little extra darkness beyond them. It is not. The planets are the compact inner region. The deeper solar system continues far beyond what most people picture. And if you use that full structure as the real standard, then leaving the solar system no longer means crossing a neat line. It means escaping a huge and very sparse region where the sun still matters. Now ask the next question directly. How far have we actually gotten by that standard? Not very far. Voyager 1 is one of the most important deep space missions ever flown. It is already beyond the heliosphere. It is often described as being in interstellar space, and even then, at its current speed, it would take hundreds of years just to reach the inner Oort Cloud, and around tens of thousands of years to get beyond the outer edge. So one of our greatest robotic escape stories is still nowhere near done, if the true finish line is the full outer gravitational domain of the sun. That changes the whole feeling of the subject. Suddenly, the issue is not whether we can get past Pluto. We already know we can do that. The issue is not even whether we can put machines beyond the sun's plasma bubble. We already know we can do that too. The issue is whether anything humans build can go far enough, survive long enough, and keep enough speed for enough time to get beyond the deepest outer structure of the solar system. That is a much harder question. So now you can see that the original question has at least 3 different answers. If the edge means the planets, we crossed it long ago. If the edge means the heliosphere, robotic probes crossed it in 2012 and 2018. If the edge means the Oort Cloud, then no human has left. No spacecraft has fully finished the job, and nothing on a human lifetime is about to do it. Same question, different thresholds, completely different conclusions, and that creates another problem. Which edge should matter most? The planetary edge matters culturally because that is the map most people grew up with. The heliosphere matters physically because it marks the limit of the Sun's outgoing plasma environment. The Oort Cloud matters gravitationally because it represents the much deeper outer domain of the Sun. None of those definitions are fake. They're just answering different versions of the same question. That is why this topic becomes so confusing so quickly. People use the phrase "leave the solar system" like it points to one event, but scientifically it can point to several. Then there is another hard truth. This is probably not going to happen in one dramatic moment. People like the idea of one future launch where a crew finally goes out and humanity officially leaves. That is probably not how this story works. The process will likely happen in stages. First, probes go farther, then more advanced probes, then maybe very fast robotic sails, there may be missions that can operate for decades far beyond the planets, and only much later, if propulsion, life support, radiation protection, autonomy, and human health all improve enough, do you start talking seriously about people going with them. That means the real story is not about one launch date. It is about removing one barrier after another until nothing blocks the mission anymore. Right now, that is not the case. Propulsion is still a barrier. Biology is still a barrier. Long-term life support is still a barrier. Power is a barrier. Radiation is a barrier. Communication delay becomes a barrier. Reliability becomes a barrier. Time itself becomes a barrier. That is why the deeper answer to the title is already clear. Humans will not leave the solar system when one crew gets brave enough. Humans will leave when the technology stack stops failing at every level at once. And that is why this question gets more serious the more carefully you define it. At first, it sounds like a basic spaceflight question. Then you realize it is really a problem of scale, then a problem of endurance, then a problem of biology, then a problem of civilization. Because once the true edge moves from Pluto to the heliopause to the Oort Cloud, you're no longer talking about a bold trip. You're talking about whether human systems can function across distances and timescales that are far beyond anything we have ever built for. So before you ask when humans finally leave, you have to ask something even more important. If our fastest probes have only crossed one boundary and are still nowhere near the deepest one, what does that say about the gap between robotic escape and human escape? So if probes already crossed one boundary, why are humans still nowhere near ready? Voyager gives you the answer, and it is not comforting. These are the most famous deep space machines ever built, and they show two things at the same time. First, getting out farther than anyone ever has is possible. Second, doing that does not mean you are anywhere close to solving human departure from the solar system. In fact, the more you look at Voyager, the more obvious it becomes that our first real interstellar hardware was never even designed for the job it ended up doing. Voyager 1 and Voyager 2 launched in 1977. Their mission was the outer planets. That was the goal. They were not built as dedicated interstellar probes, and they were definitely not built as a test for what it takes to carry humanity into deep space for generations. But history does not care what the original plan was. Voyager 1 became the first human-made object across the heliosphere, and Voyager 2 became the second. On the way, they changed planetary science. They revealed new details about rings, moons, magnetic fields, radiation environments, plasma conditions, and the overall structure of the outer solar system. So right away, Voyager gives you one big lesson. A machine does not have to be built as a star mission to become the first thing that begins leaving home. That sounds inspiring, and it is, but it also points to a harder truth. Humanity's first real departures may not begin with a giant starship or a mission that looks historic from the start. They may begin with smaller systems built for more limited purposes that just keep going because the hardware survives. That matters because a lot of people still think the road to interstellar travel starts with some dramatic leap. Voyager suggests something more uncomfortable. The road may start with endurance, not grandeur. Not with a miracle vehicle, but with a machine that lasts longer than expected. then comes the next problem. Voyager sounds fast until you compare it with the actual scale of interstellar distance. NASA says Voyager 1 is escaping the Sun at about 3.5 astronomical units per year, and Voyager 2 at about 3.1 astronomical units per year. Those numbers sound strong if you stay inside the solar system. They really are strong by the standards of planetary missions. But once you bring in a light year, the whole picture changes. Voyager 2 moves at around 15.4 kilometers per second, and at that speed it would take about 19,390 years to travel 1 light year. That is the number that destroys casual talk about human interstellar travel. A lot of people hear near a star and think of a very long trip. That is still too small. At Voyager speed, the nearest stars are not realistic destinations for any mission that needs to matter within human history. A light year is not just a large unit. It is the point where normal mission thinking breaks down. Alpha Centauri is just over 4 light years away. So now do the emotional math in plain language. Even one of the greatest deep space spacecraft ever built, already beyond the heliosphere, is moving so slowly on the interstellar scale that another star system still sits at the edge of timescales longer than recorded civilization. That is why Voyager is both impressive and discouraging. It proves escape from the inner solar system is real. It also proves the stars are still effectively out of reach. So does that mean speed is the whole problem? Not exactly. And this is where Voyager teaches the opposite lesson. The real challenge is not only how fast you go, it is whether your system can still function after decades in interstellar space. These probes are still operating because engineers have kept them alive through hardware degradation, software trouble, thermal issues, and shrinking electrical power. NASA says each Voyager loses about 4 watts of power per year, and as of April 2026, both spacecraft were still functioning, even though mission teams have had to turn off heaters and instruments to extend their lives. That changes the whole discussion. Deep space is not just about reaching a high number on a speed chart. It is about building something that can survive long enough for distance to start shrinking at all. That point gets overlooked all the time. People jump straight to exotic engines, giant velocities, and the dream of getting somewhere quickly. Voyager reminds you that long-range exploration is also a slow fight against failure. Power drops, systems age, temperatures become a threat, components go out of spec, communication gets harder, and the farther you go, the less help you can expect. In that kind of environment, raw speed by itself is not enough. A fast machine that dies early does not solve anything. A slower machine that keeps working for half a century can change history. That is not a side lesson. That is one of the central lessons. Then Voyager makes the point even harder by exposing how old its technology really is. Its onboard computers are extremely limited by modern standards. NASA has pointed out that Voyager's computers process about 8,000 instructions per second, while a modern smartphone operates at more than 14 billion instructions per second. That comparison sounds ridiculous at first, but that is exactly why it matters. Human-made hardware reached interstellar space using computing power that looks primitive next to an everyday consumer device. That does not mean interstellar travel is easy. It means something more important. The first real requirement for interstellar exploration is not brilliance in one machine. It is reliability across decades. That is a very different standard from how people usually picture future space travel. People imagine the breakthrough as something sleek, advanced, powerful, and almost perfect. Voyager suggests the first real interstellar technology is something less glamorous. A system that refuses to stop functioning. A system that can tolerate failure, accept degradation, operate with limited resources, and still produce useful results decades later. That is why Voyager still matters so much. It did not win because it was futuristic by today's standards. It won because it was durable enough to outlast expectations, and that leads to the main paradox. Voyager proves you can cross one meaningful boundary of the solar system with 20th century technology. That is real. It happened. No one can take that away, but Voyager also proves that crossing that boundary does not get you close to another star, and it does not get you beyond the sun's full outer domain on anything close to a human timescale. So the same mission gives you two opposite conclusions. We already began leaving, we are still nowhere near gone. That is the rhythm that should stay underneath the whole story. Every time you think the answer is arriving, the scale problem returns. Every time you think the scale problem makes the mission impossible, Voyager reminds you that hardware can survive much farther and longer than people once expected. So the lesson is not optimism or pessimism by itself. The lesson is that human readiness is being measured against the wrong standard if you only look at a boundary crossing. Voyager crossed a boundary. Humans still cannot follow. Not because the path is unknown, but because the difference between a probe and a human mission is enormous. A probe can survive with a tiny power budget. A human mission cannot. A probe can drift for decades with limited processing and no life support. A human mission cannot. A probe can accept system degradation as long as a few core instruments still work. A human mission cannot. Once people are on board, every demand rises at once. Power rises. Mass rises. Reliability requirements rise. Radiation becomes a direct biological problem. Life support becomes continuous. Repair becomes critical. And mission duration stops being an engineering inconvenience and becomes a medical and social threat. So Voyager already started the countdown. But not in the way most people think. It did not begin the countdown to human starflight. It began the countdown to a harder realization. We now know enough to say the first part is possible. We can send machines beyond the planets. We can even send them beyond the heliosphere. But we also know enough to say that doing this with human beings is not just the same problem at a larger size. It's a different class of problem. And once you accept that, the next question gets even more serious. If our best deep space survivors are still this slow, this fragile, and this dependent on decades of careful nursing just to keep working, then what happens when the payload is not a probe, but a human body that has to stay alive the entire time? The problem is not just that space is big. The problem is that almost everyone is still thinking on the wrong scale. Most people talk about the solar system as if it is basically the sun, the planets, and then empty space after that. That is not what it is. The planets are only the compact inner region. They are the part we know best because they are bright, structured, and easy to put on a diagram. But the solar system keeps going far beyond them. Pluto sits out at around 30 to 50 astronomical units from the Sun, which already sounds extreme by normal standards. Then the heliopause is much farther out. Then beyond that, the Oort Cloud may begin thousands of astronomical units from the Sun and continue outward for tens of thousands more. So the part people usually mean when they say the solar system is actually just the dense central region. The full structure is vastly larger and much more spread out than most people think. That changes the question immediately. If the real solar system includes those outer regions, then leaving it is not just doing a slightly harder version of planetary exploration. It is a different class of journey. Going from Earth to Mars is one kind of mission. Going from Earth to Jupiter is a much harder one. Going past Pluto is harder again, but trying to go beyond the full outer reach of the Sun is not just the next step in that sequence. It is the point where the map changes category. You are no longer talking about moving between major objects in a relatively organized system. You're talking about crossing a vast outer domain, where distance itself becomes the main obstacle. And the clearest way to understand that is to stop thinking about spacecraft for a second and think about light. Light moves so fast that on human scales it feels instant, but even light needs time to cross the solar system. Sunlight takes a little over 8 minutes to reach Earth. That already tells you Earth is not next to the Sun in any everyday sense. Then go farther out. It takes around 4.5 hours for sunlight to reach Neptune's orbit. To get beyond the heliopause, you're talking around 17 hours. And if you start asking about the Oort Cloud, then now the crossing time for light itself stretches into days, and depending on what edge you mean, even more than a year. That is the point where your intuition should stop trusting itself. Because if even light does not cross this territory instantly, then anything carrying mass has a much worse problem. A spacecraft is not a beam of light. A human habitat is not a beam of light. Once you feel that difference clearly, the entire topic becomes more serious. You're not just asking whether we can build a stronger rocket. You're asking whether we can move matter, machinery, energy systems, and living bodies across a space so large that even nature's speed limit needs meaningful time to cross it. And this is still only the solar system. At this stage, you have not even aimed at another star yet. Then comes one of the most misleading phrases in astronomy, the nearest star system. Alpha Centauri is just over 4 light years away, and because it is the nearest star system outside our own, people hear that and feel a kind of relief. Nearest sounds hopeful. It sounds like maybe this is the first realistic destination. But in engineering terms, nearest does not mean accessible. It means less impossible than the others. That is a huge difference. Alpha Centauri is about 25 trillion miles away. That is not a travel problem in the ordinary sense. That is a scale problem so extreme that the language starts hiding the reality from you. This is where the vocabulary itself becomes dangerous. We say nearby stars, we say neighbouring systems, we say potentially habitable worlds. Those phrases are scientifically normal, but they can trick your instincts. These are not neighbours in the human sense. They are not destinations in the way people use that word for planets or moons inside our own system. They are targets that only matter to a civilization that has already solved propulsion, power, radiation shielding, long-term life support, autonomy, and mission planning across us decades or centuries. Once you say it plainly, the issue becomes obvious. A nearby star is still unimaginably far by any standard that matters to a crewed mission. Then someone usually says, but our spacecraft are already incredibly fast. That sounds reasonable too, until you look at the numbers. Parker Solar Probe has reached around 430,000 miles per hour, or about 687,000 kilometers per hour. That is an astonishing human achievement. Inside the solar system, that speed is extraordinary. It is not fair to call it anything else. But when you compare that speed to Alpha Centauri, the result is still brutal. Even at that scale of velocity, the trip would still take thousands of years. So yes, we are fast by solar system standards, and yes, we are still extremely slow by interstellar standards. That difference matters more than people think. It is not a small performance gap. It is not something you close with a modest upgrade, a better fuel mix, or one impressive engine. It is the difference between a mission people can plan and a commitment that can outlast governments, institutions, languages, and maybe entire eras of human history. A trip that takes months or years can still be managed within one system, one generation of engineers, and one chain of command. A trip that takes centuries or longer becomes something else. It becomes a historical project, not just a technical one, and this is the moment where the whole story changes scale. Up to this point, it is easy to think the question is just, can we build a better spacecraft? But once you actually feel the distances, you realise that is not enough. The real question becomes much harder. Can humans build systems that still function when rescue is impossible? Can you build a ship that can survive when spare parts are limited, failures accumulate and no quick return is possible? Can you keep a crew alive when communication delays eventually stop Earth from being useful in real time? Can you maintain a mission when the people who launched it may be gone long before it reaches its destination? That is why the scale problem is not just physics. It starts with astronomy, but it does not stay there. Once distances become this large, everything else gets pulled in. Biology matters because human bodies fail in deep space. Economics matters because systems this large need decades of funding and industrial support. Psychology matters because isolation, delay, and confinement become mission threats. And time matters because the longer a mission lasts, the more chances there are for technology, culture, and priorities on Earth to change completely. So the real shift in this section is simple. At first, leaving the solar system sounds like a transportation problem. Then the numbers force you to see that it is actually a systems problem. A distance problem becomes a survival problem. A rocket problem becomes a civilization problem. Because once the scale gets large enough, it is no longer enough to ask whether a spacecraft can move that far. You have to ask whether everything connected to that spacecraft can remain functional, meaningful, and supported for the entire duration. And that is why this topic gets more disturbing the more accurately you explain it. The planets are not the outer wall. Light itself takes serious time to cross the outer solar system. The nearest star is only close because every other option is worse. Even our fastest spacecraft barely make a dent in the real interstellar distance problem. So by the time you ask whether humans can leave, the honest version of the question is no longer, can we go far? It is, can anything carrying human life remain alive, stable, and purposeful across distances that break every normal assumption about travel? And once that becomes clear, the next part hits even harder. If scale alone already makes the stars feel almost unreachable, then what happens when you look at the engines we actually use now and ask whether they were ever capable of solving this in the first place? So if the scale is already this bad, what happens when you look at the engine we actually use now? The answer is simple and brutal. Chemical rockets got humanity into space. They got us to the moon. They got probes to the outer planets. They are one of the greatest technologies ever built. But they are not getting human beings to the stars. Not because they failed, and not because they are weak, but because the job they solved is much smaller than the job people now want them to solve. That part matters. It's easy to talk about chemical propulsion like it is old technology that we outgrew. That is wrong. Chemical rockets did the first hard part. They got us out of Earth's gravity well, and that is a huge achievement. New Horizons is a perfect example. It left Earth at about 58,536 kilometers per hour after launch and boost, which was the highest launch velocity ever reached by a human-made object relative to Earth at the time. Then Jupiter added another major increase through gravity assist. That was enough to send it past Mars, past Jupiter, all the way to Pluto, and then beyond into the Kuiper belt. That is not a weak system. That is a system powerful enough to open the solar system. So the problem is not that chemical propulsion cannot go far. It clearly can. The problem is that interstellar distance makes even our best chemical performance look local. That is the real shift you have to make. A rocket that can cross the planetary region still looks tiny when the target is not Pluto, not the heliopause, not even the Oort Cloud, but another star. Chemical propulsion wins by delivering a huge burst of energy over a short time. That is exactly why it is so good for launch and escape. But that same strength becomes a limit when the mission stops being about escaping one gravity well and starts being about building velocity for a journey that may last longer than anything human civilization has ever attempted. And then the hard math shows up. Even if you never say it directly, every time you want more speed from a chemical rocket, you pay for it with more propellant. Then you need more propellant to carry that extra propellant. Then you need more tank structure to hold it, more engine performance to move it, and more total mass just to support the whole stack. This is why chemical rockets start to punish ambition. They are excellent when the goal is a short, violent push. They are terrible when the goal is sustained acceleration over huge distances. Chemistry can throw you free of Earth. It cannot cheaply drag a full human habitat toward another star. That is the part people often miss. They think the problem is just scaling up. Bigger rocket, bigger tanks, bigger mission. But with chemical propulsion, scaling up quickly becomes self-defeating. The more you ask from it, the more mass the system has to carry, and the more of that mass becomes fuel just to move fuel. That spiral is why chemical propulsion becomes trapped. It is amazing inside its proper regime. Outside that regime, the cost rises faster than the dream. Once the payload is large and the target is truly interstellar, the numbers stop looking ambitious and start looking absurd. So maybe gravity assists fix that, right? They are real. They work. They are some of the smartest trajectory tricks ever used in spaceflight. New Horizons got to Pluto faster because Jupiter gave it a boost. Voyager reached the outer solar system and then the heliosphere using planetary alignment and gravity assist geometry in a way that was almost unbelievably effective. So yes, gravity assists are brilliant, but they are not magic. They do not create free escape from the deeper problem. They only let you borrow motion from planets that already exist inside your home system. That limitation matters a lot. Gravity assists depend on timing, alignment, launch windows, and available massive bodies in the right places. You cannot just request one whenever you want. And even when they work perfectly, they're still tied to the structure of the solar system itself. They help you move through home more efficiently. They do not solve the much bigger speed problem once you leave home behind. That is the key point. Gravity assists are incredible for surfing the architecture of the solar system. They are not a real answer to interstellar travel. They help you get out cleaner and faster. They do not turn the stars into practical destinations. And then the situation gets much worse the moment human beings enter the vehicle. A robotic probe can be tiny. It can be cold. It can survive with low power and limited shielding. It does not need air, water recycling, medical support, food, exercise systems, pressure control, thermal comfort, or protection from long-term isolation. A human mission needs all of that. The second you put people on board, the mass problem explodes. Now you are not launching instruments. You're launching a moving habitat. You're launching a life support machine. You're launching a system that has to protect biology, not just electronics. That means the ceiling for chemical propulsion becomes obvious very quickly. The same kind of rocket that can throw a compact robotic craft into deep space becomes deeply inadequate when the payload is a pressurized environment full of human bodies that need continuous support. You need structure. You need redundancy. You need shielding. You need water systems, oxygen systems, waste systems, food storage or production, medical hardware, repair tools, spare parts, and fault tolerance across years or decades. And all of that mass has to be accelerated. Once you see the payload clearly, the idea of using chemical rockets as the main answer to human solar system departure stops sounding bold and starts sounding outdated. That does not mean chemical propulsion is obsolete. It means it is trapped in the wrong part of the problem. It is still essential. We still need it for launch. We still need it for maneuvers. We still need it for many missions throughout the solar system. Chemical rockets are not bad technology. They are foundational technology, but they stop being the full answer once the question becomes, when will humans finally leave the solar system? At that point, chemistry becomes the opening move, not the solution. It gets you off the ground. It gets you out of the gravity well. It may get you onto the first outbound trajectory, but then something else has to take over, because chemistry cannot carry the whole mission by itself. And that is where the pressure starts building. If the scale is too large for ordinary travel thinking and chemical rockets are only good for the first part of the trip, then the real question is no longer whether they can be improved. The real question is what comes after them. What propulsion system actually changes the game enough to matter? What system is strong enough to move human missions deeper into space without collapsing under its own mass penalty? And once you ask that, the next stage of the story begins, because now you have to look at the first technology that really tries to move beyond the chemical ceiling. So if chemical rockets are the handoff point, what is the first propulsion system that actually changes the discussion? The answer is nuclear. And this is where the story gets more serious, because nuclear propulsion is not just a science fiction word people throw around when normal rockets stop looking good enough. It is a real engineering path, and it matters because it moves you into a different performance range. But it also creates a new problem. Nuclear propulsion can make deep space human missions much more realistic and still leave interstellar travel very far away. Start with nuclear thermal propulsion. The reason it matters is simple. It can get much more performance from the same basic idea of carrying propellant and throwing it out the back. In a chemical rocket, you get a hot exhaust from chemical reactions. In a nuclear thermal rocket, a reactor heats the propellant directly, and that can push performance to roughly double what the best traditional chemical systems can do. That is a major jump. It is not a small improvement, and it is not the kind of gain you ignore. When you're talking about human missions in deep space, doubling that part of the performance changes mission design in a real way. That is why serious plans for future crewed missions, especially Mars-class missions, keep coming back to nuclear thermal propulsion. Once the mission gets longer, the value of faster travel becomes obvious. Shorter trip time means less time exposed to radiation. It means fewer supplies have to last as long. It means less time for systems to fail. and less time for the crew to be trapped in transit. So nuclear thermal propulsion is not exciting because it suddenly makes starflight easy. It is exciting because it can make hard missions much less punishing. That alone is enough to matter. And this is not just theoretical talk anymore. The reason nuclear propulsion now feels different from a lot of older future tech ideas is that major institutions are treating it as an actual program area, not just a distant concept. NASA and DARPA announced plans to develop and demonstrate advanced nuclear thermal propulsion technology, with the idea tied directly to future crewed Mars missions. That changes the tone of the whole topic. Once an idea moves from papers and speculation into real development planning, it crosses an important line. It does not mean success is guaranteed. It means the conversation has shifted from "would this ever matter?" to "how far can this realistically go?" That is the key escalation here. Chemical propulsion built the age of launch, orbit, and planetary exploration. Nuclear propulsion is being positioned as one of the technologies that could build the next stage, the stage where humans start pushing deeper into the solar system without paying such a severe time penalty. That is a real step forward. It means the question is no longer just how to escape Earth. It becomes how to move human missions through space more efficiently once they are already out there. That is a different kind of capability. But nuclear propulsion does not come in just one form, and the other main branch is even more important for understanding where this might go next. Nuclear electric propulsion works very differently. Instead of using a reactor to heat propellant directly for one powerful push, it uses nuclear power to run electric thrusters over very long periods. That means the thrust is much lower, but it can continue for a huge amount of time, and that difference matters. Chemical rockets are violent and brief. Nuclear electric systems are slower, but they can keep working. For deep space missions, that is a completely different philosophy. That is why nuclear electric propulsion keeps showing up in serious long-duration concepts. If you can generate enough onboard power and keep the system running reliably, then steady thrust over months or years can build major mission value. For robotic precursor missions or cargo missions, that can be transformative. Even for human exploration, high-power electric propulsion starts to look attractive because it trades short bursts for long-term efficiency. The point is not spectacle. The point is sustained performance. And once you are talking about large distances, steady performance matters more than dramatic launch energy. But this is also where the limit becomes clear again. Even advanced nuclear electric concepts being studied now are mostly aimed at Mars-class missions or deeper solar system missions, not true interstellar travel. They help at the scale we are just beginning to struggle with. They do not solve the next scale beyond that. This is the pattern that keeps repeating. Every time a propulsion system gets good enough to make one impossible mission start looking plausible, the next layer of distance immediately appears and makes that improvement look smaller again. That is the harder truth about nuclear propulsion. It solves one bottleneck by exposing the next one. Yes, if you cut interplanetary trip times, that changes everything for missions to Mars and probably for missions deeper into the outer solar system. Less transit time means less radiation dose. Less time means fewer consumables. Less time means lower medical and psychological stress. It narrows the window in which everything can go wrong. That is a massive benefit. And for real human spaceflight, those benefits are not secondary. They are mission-defining. But then you step back and ask the larger question. Does any of this make Alpha Centauri remotely close? No. Does it make a human mission beyond the heliosphere look easy? No. Does it make leaving the solar system in the Oort Cloud sense suddenly practical? No. What nuclear propulsion gives you is breathing room inside the solar system. It gives you more credible deep space mission architecture. It gives you a chance to move humans farther, faster, and with better margins. That is a major achievement. It is just not the same as solving interstellar travel, and that distinction is the most important part. Nuclear propulsion is not the destination of this story. It is the middle of the story. It is probably one of the technologies that gets humans much deeper into the solar system than chemical rockets can manage on their own. It may support better precursor missions, more ambitious habitats, faster crewed travel to Mars, and eventually missions that push far beyond Mars with a level of confidence we do not have now. That matters a lot, but it still does not close the gap between deep space and another star. So when people hear nuclear rocket, they often think the problem is basically solved. It is not. The problem is refined. That is the more accurate way to say it. Nuclear thermal propulsion improves the performance regime. Nuclear electric propulsion changes the mission profile. Together they can make much harder missions possible, but they do not erase the deeper fact that interstellar distances are still on a different scale from everything these systems are currently meant to handle. And that is why this section should make the tension rise, not fall. Because nuclear propulsion is the first answer in this story that feels big enough to matter and real enough to take seriously. It is not fantasy. It is not just a concept people mention when they want to sound futuristic. It is one of the few pathways that can genuinely push human missions into a new range. And even then, it still leaves the main question standing. If a major propulsion upgrade still only gets you from barely possible to more manageable inside the solar system, then what kind of idea do you need before interstellar travel stops sounding completely unreasonable? That is where the next step becomes important. Because after nuclear propulsion, the first concepts that start to sound like they belong in an actual interstellar roadmap do not run on fuel in the usual sense at all. So what is the first propulsion idea that actually starts sounding like interstellar travel instead of just better deep space travel? This is where sails enter the story, and this is the first time the conversation really changes. Because now you are no longer asking how much fuel you can carry, you're asking whether you can move a spacecraft using light itself. That sounds strange at first, but this part is not theoretical in the loose sense. Light can push matter. Not in a dramatic way, not with the kind of force people are used to thinking about, but in a real measurable way. And once you accept that, a whole new class of propulsion opens up. NASA's Advanced Composite Solar Sail System is important for exactly that reason. It is not just a concept on paper. It is a real technology demonstration. The basic idea is simple. Sunlight carries momentum. When that light hits a reflective sail, it pushes on it. The force is tiny, but it is there. And in space, a tiny force that never stops can matter more than people expect. A rocket burn ends. A sail does not need to stop as long as light is hitting it, and the craft is still set up to use that push. That is what makes sails different from almost every propulsion system people usually picture. And this is the first time the logic starts pointing naturally beyond the solar system instead of just farther into it. Chemical rockets are amazing for launch and escape. Nuclear systems can extend how far and how fast you can move through deep space. But sails introduce a different way of thinking. Instead of carrying huge amounts of propellant and spending it, you build a very light system and let an external energy source keep pushing it. For solar sails, that source is sunlight. The acceleration is small, but the propellant cost is basically zero. For robotic missions, that is a very attractive trade. That does not mean solar sails solve the human problem. They do not. The pressure from sunlight is weak, which means the sail has to be very large and the payload has to stay very light if you want meaningful performance. That is manageable for small robotic systems. It becomes much harder for anything massive. A human vehicle is heavy before you even add shielding, supplies, life support and redundancy. So solar sails do not suddenly make crude interstellar travel practical. But they matter because they are the first propulsion family in this whole discussion that genuinely starts to lean in the right direction. Then comes the more aggressive version. And this is where the flaw really shifts. The more serious interstellar concept is not using sunlight. It is using a powerful beam of light sent from a controlled source, usually imagined as a large laser array. Instead of waiting for the natural pressure of sunlight, you drive the sail with a much stronger beam and force it to accelerate much harder. That is the logic behind laser sails and concepts like Breakthrough Starshot. The goal there is not to shave time off a Mars mission or make the outer planets easier. The goal is to push an ultralight spacecraft to a meaningful fraction of the speed of light. That is the first idea in this topic that starts making interstellar travel sound like something you can discuss without immediately falling into timescales of thousands or tens of thousands of years. If you can accelerate a tiny spacecraft to around 20% of the speed of light, then Alpha Centauri stops looking like a destination for the far future and starts looking like a target a probe could reach in decades. That is a completely different category of possibility. It does not solve the human mission, but it changes the roadmap. Suddenly you are not limited to saying, maybe one day. Now you can say, a robotic precursor might actually get there within a useful amount of time. That is why laser sails matter so much. They are not just faster versions of existing spacecraft. They break the pattern that has limited every other propulsion system in this story. With chemical rockets, the mass penalty gets ugly fast. With nuclear systems, the distances are still overwhelming. But with laser sails, at least for tiny payloads, you start entering a speed regime where interstellar missions become short enough to fit inside scientific planning instead of a mythology. That is a major threshold. But the fine print is severe, and this is where you have to stay honest. Starshot-class concepts are not talking about crude ships. They are talking about extremely small probes, basically gram-scale systems. That difference is everything. It is much easier to imagine accelerating something tiny to enormous speed than it is to do the same with a human habitat. The beam power required is extreme. The sail material has to survive intense heating. The system has to stay stable under acceleration. The pointing accuracy has to be almost absurdly precise. And all of this has to happen over vast distance with almost no tolerance for error. Then there is the arrival problem, which is one of the hardest parts. A tiny probe moving at a major fraction of light speed does not really get to slow down in any easy way. It does not arrive and enter orbit and begin a calm scientific survey. It flies through the target system incredibly fast. That means a lot of these early laser sail missions would be flyby missions, not settlement missions, and not even traditional exploration missions in the way people normally imagine them. They would gather data during a very brief passage and send it back if they can. That is still revolutionary, but it is a very specific kind of revolution. So no, laser sails do not give you a human ship. Not now, not even close. In the near term, they look much more like high-speed robotic scouts than anything carrying people. They are closer to precision scientific projectiles than to starships. That may sound disappointing, but it should not. Because even that changes the picture in a big way. Once you can send a microscopic payload across interstellar distance in decades rather than millennia, the entire sequence of future exploration starts to reorganize itself. Now you can imagine sending precursor probes ahead of any human mission. You can imagine mapping the local environment around nearby stars. You can imagine checking for hazards, studying planets directly, measuring dust, plasma, magnetic conditions and radiation before anyone even starts talking seriously about sending people. You can imagine replacing blind ambition with real reconnaissance. That matters because one of the biggest problems with human interstellar travel is that right now it is mostly a mission to the unknown. Laser sails offer the first serious path toward changing that. And that is why sails belong in this story even though they do not solve the human problem by themselves. They are the first propulsion architecture here that does not just make deep space travel somewhat better. They create a real interstellar precursor option. They turn starflight from a distant wish into something that at least begins to look testable on the robotic level. That is a huge step. It means the first phase of true interstellar exploration may not be humans leaving at all. It may be tiny machines going first and telling us what is actually out there. So the tension rises again, because now the problem is no longer just speed. For the first time, there are ideas that can make interstellar distance look less impossible for very small payloads. But that creates a harder question. If even the first plausible starbound systems only work by shrinking the payload down to something almost microscopic, then what kind of propulsion do you need if you want something much bigger than a wafer and a sail? So if sails can only really help tiny probes, what do you even look at next? This is where the ideas start sounding extreme, but they keep showing up for a reason. Once you get serious about interstellar distance, ordinary propulsion keeps failing the test. Chemical systems run into mass problems. Nuclear systems help, but they still do not close the gap. Sails can work for very light payloads, but that does not get you a human ship. So the same two ideas keep returning in serious discussions: fusion and antimatter. Not because they are fashionable, but because once you push the numbers hard enough, lower energy options keep coming up short. Fusion stays in the conversation because it attacks the problem at a deeper level. It is not just about going faster for the sake of going faster. It is about entering an energy regime where the mission math stops looking completely hopeless. That is why fusion keeps reappearing whenever anyone talks seriously about reaching the outer heliosphere, the local interstellar medium, or anything beyond that. NASA-backed concept work has treated fusion as a possible path toward rapid exploration of the heliosphere and beyond. That word beyond matters. It is not there for effect. It is there because once you move past the ordinary solar system scale, propulsion ideas with less energy density start looking too weak. And fusion matters for another reason that people often miss. It is not only attractive because it could make a spacecraft move faster. It is attractive because it could let a spacecraft do more than just launch, coast, and hope. A serious deep space or interstellar mission is much more valuable if it can actually maneuver. It matters if you can change course. It matters if you can manage thrust over time. It matters if you can speed up when needed and slow down in ways that preserve the mission. That is one of the biggest hidden problems in interstellar thinking. A lot of mission concepts sound impressive until you realize they mostly describe a projectile. Launch, drift, arrive too fast, and then the mission is basically over. Fusion stays attractive because it points towards something more capable than that. That is what makes it feel like more than just another bigger engine. In theory, fusion could offer high delta V and mission flexibility at the same time. It hints at a spacecraft that is not just being thrown into deep space, but one that can still make choices once it gets there. That is a huge difference. If you ever want real exploration beyond the solar system, not just a one-pass stunt, then some degree of control in deep space becomes essential. A mission that can only rush outward is limited. A mission that can operate, adapt, and possibly slow down starts to look like actual exploration. But then the next idea is even more extreme. Antimatter never disappears from these conversations because on paper, it is the purest energy answer. Matter-antimatter annihilation releases more energy per unit mass than anything else people talk about in propulsion. That is why it keeps coming back. If you only looked at raw energy density, antimatter would sound like the obvious winner. It is the kind of idea that makes every other propulsion system look limited. And that is exactly why it is so dangerous to talk about casually, because the physics is powerful enough to sound like a cheat code. Then engineering ruins the fantasy almost immediately. The same literature that makes antimatter sound incredible also makes it sound nearly impossible to use. The cost is absurd, the handling problem is absurd, the shielding problem is brutal. Once you start dealing with annihilation products and high-energy radiation, the entire design begins to bend around containment, protection, and survival. The energy is real, but so is the punishment for trying to manage it. That is why antimatter sits in such a strange place. It is the cleanest answer in basic physics terms, and one of the dirtiest answers in practical engineering terms. So the honest way to describe both fusion and antimatter is this: they are not fake. And they are not remotely mature. That distinction is important. These are not nonsense ideas. They are not just there to decorate documentaries and make the future sound dramatic. They have real physical logic behind them. They show up in real studies for good reasons. When the scale problem gets honest enough, these ideas stop sounding ridiculous and start sounding almost necessary. But when the engineering gets honest enough, they still look very far away. That tension is exactly what makes this part of the story so important. Fusion and antimatter live in the zone between credible concept and usable hardware. And that zone is where many space dreams get stuck for a very long time. The idea works in principle. The physics does not laugh you out of the room. Serious people still study it. But the path from principle to machine is huge, expensive, dangerous, and full of systems-level problems that do not care how elegant the idea looked at the start. That is why you should not treat these propulsion concepts like fantasy, but you also should not talk about them like they are waiting in a warehouse for the next launch window. And once you reach this point, the whole subject stops being just about engines. That is the deeper shift. If the propulsion system you need is powerful enough to sound like fusion or antimatter, then the real question is no longer just, can we design it? The real question becomes, what kind of civilization could actually build it, fuel it, test it, shield it, maintain it, and trust people to use it? That is a much larger question. It brings in industry, energy production, safety systems, manufacturing scale, long-term funding, and risk tolerance at a level humanity has never sustained in space. That is the fracture line in the starflight debate. It may not be true that we are blocked because nobody has thought of the right engine. It may be that we are blocked because the kinds of engines that start to make interstellar travel look less impossible, demand an industrial base and a level of long-term coordination that we do not yet have. A fusion-driven mission is not just a better spacecraft. It implies a civilization strong enough to support that spacecraft from concept to launch. An antimatter mission would demand even more. At that point, the limiting factor may not be invention. It may be whether human society can stay organized around a project that large for long enough to make it real. And that is why this part of the story should increase the tension, not release it. Because now the answer is getting sharper. We are not just waiting for one breakthrough engine to save us. We are running into a deeper limit. The more powerful the propulsion concept becomes, the more it depends on power systems, industrial capacity, and governance that go far beyond one mission. Interstellar travel starts to look less like a triumph of one spacecraft and more like a test of whether a civilization can hold together around extreme technology for decades. So now the problem gets even more uncomfortable. Suppose somehow you do get the propulsion. Suppose you find a way to move much faster and push much farther. That still does not answer the next question. Because a starship does not only need an engine, it needs people, and human beings bring their own failure modes into the mission. So what if you solve the engine and still lose the crew? That is the next wall. People talk about propulsion like the ship is the mission, but for a human journey out of the solar system, the body is the real problem. The body is not cargo. It is the most fragile system on board. And the worst part is that space does not need centuries to start damaging it. Space is already dangerous on missions far shorter than anything interstellar. Start with radiation. This is not some distant problem for future starships. It is already a mission-limiting problem for Mars-class travel. On the cruise to Mars, Curiosity measured about 1.8 millisieverts of galactic cosmic radiation per day. NASA's own standards put astronaut career exposure limits below 600 millisieverts, and their planning numbers for free space are already tight enough to shape mission design. That means even before you say the words interstellar mission, the exposure problem is already serious. Once you do say it, the numbers become brutal. A human trip beyond the solar system would mean long periods in deep space where the crew is exposed not for months, but potentially for years or much longer. That pushes radiation from a difficult engineering problem into something much closer to a biological veto. And it is not just cancer risk in the abstract. Radiation affects the nervous system, tissue damage, long-term health, and possibly performance. That is what makes it so dangerous for a deep mission. You are not only trying to keep people alive long enough to arrive, you are trying to keep them functional while they are travelling. A crew that is technically alive but cognitively impaired, medically weakened, or physically degraded is not a successful crew. So the radiation issue is not a box you check with thicker walls and then move on. Every kilogram of shielding raises mass. Every mass increase hurts propulsion, and every gap in shielding turns into accumulated biological risk. Then comes microgravity, and this is where the problem gets even more physical. NASA has found that astronauts can lose around 1% to 2% of bone density per month in key areas, like the hip and spine during long stays in reduced gravity. That is an extreme rate of deterioration. On Earth, age-related bone loss happens much more slowly. In space, the body starts acting like gravity no longer matters, because it does not. Bones that are not being loaded the way they evolved to be loaded begin to weaken. This is not a small health issue. It is the skeleton being slowly pushed in the wrong direction by the environment itself. That changes how you have to think about the ship. A ship leaving the solar system is not just carrying humans through space. It is actively fighting against the environment every day just to stop those humans from physically breaking down. Bone loss is not passive. Muscle loss is not passive. Fluid shifts are not passive. Deconditioning is not passive. If the mission extends from months into years, the crew is not simply waiting to arrive. Their bodies are continuously adapting to the wrong world unless the spacecraft keeps forcing the right conditions back onto them. And exercise, while necessary, is clearly not enough on its own. Even on the International Space Station, crews have spent many hours per week exercising and still lost bone density and muscle mass. That matters because it destroys one of the easiest comforting assumptions people like to make. You cannot just put a treadmill and a resistance machine on a ship and assume the biology problem is solved. Exercise helps, but it does not restore Earth. It does not fully replace gravity. It does not erase the medical problem of extended life in an environment human beings were never built for. So now the question gets harder. If exercise is not enough, what do you add? Artificial gravity, rotating habitats, short periods of centrifuge exposure, constant medical monitoring? The answer may be some combination of all of them, and that is exactly what makes the problem so serious. A human mission leaving the solar system is not one clean engineering stack. It is propulsion plus life support plus medicine plus long-term countermeasures, all working together. The crew does not just need to survive, they need to stay strong enough to operate the ship, repair the ship, make decisions, and deal with emergencies long after launch. And even artificial gravity, which people often treat like the obvious solution, is nowhere near as simple as it sounds. A spinning ship sounds easy when you say it fast. In reality, the details matter a lot. How much artificial gravity do you need? How long does the crew need to be exposed to it each day? How large does the rotating radius have to be before it becomes tolerable and medically useful? How much motion sickness or stress does it create? What level of G is enough to protect bone and muscle, circulation and balance? These are still active research questions. We are not at the stage where artificial gravity is just waiting to be installed like a standard spacecraft feature. That is the deeper warning. Even some of the most basic health countermeasures for long missions are still being studied in analog environments on Earth. That means people who talk casually about spinning interstellar habitats are skipping over the fact that the underlying biomedical rules are still not fully nailed down. We do not yet have the kind of certainty you would want before locking human beings into a vehicle for years or decades. And if that sounds like a small missing piece, it is not. It is a mission-critical unknown. Then widen the frame even more. Long missions are not just about bones and radiation. They are about sleep quality, immune function, mental performance, stress regulation, infection risk, healing, metabolism, and the way all of those systems interact over time in isolation. NASA's human research work keeps returning to these issues because they are not solved. Even lower gravity and microgravity effects on biology are still active research areas. That should tell you everything. Humans are not yet a finished deep space payload. We are still being studied as one. That is the point that should hit hardest in this section. A lot of people think the human mission starts once the engine exists. In reality, the mission starts once the human body stops being the weakest link. Right now, that is not where we are. Right now, our bodies are still highly tuned for Earth conditions. Gravity, atmosphere, magnetic protection, quick medical help, stable day-night cycles, and a biosphere doing most of the support work for free. Strip those away for long enough, and the body starts paying a price very quickly. So when people ask when humans will leave the solar system, they usually picture the problem as a transportation problem. It is not. It is a survival problem. And survival here is not just about not dying. It is about staying medically stable, physically capable, mentally sharp and operationally useful across an environment that continuously works against the human design. That is why the body is not a passenger. It is the weakest subsystem on the mission, and every kilometre outward makes that more obvious, and that pushes the story into the next stage. Because even if you could protect the crew and keep the biology under control, there is still another question waiting. A human being does not just need shielding and exercise. A human being needs an environment. Air, water, pressure, waste handling, oxygen, recovery systems, maintenance, food, redundancy. So the next problem is even bigger than the body itself. If the crew cannot live directly in space, then the ship has to become something much more than a vehicle. So what if you protect the crew's body, but the ship itself cannot keep life going? That is the next problem, and it is bigger than most people realize. A real starship is not just a vehicle with seats, engines, and supplies. It has to behave like a closed world. The farther you get from Earth, the less your spacecraft acts like transportation, and the more it acts like an artificial environment that has to keep rebuilding the conditions of life from inside itself. If that system breaks, it does not matter how fast the ship is going. This is why the International Space Station matters much more than people think. A lot of people see the ISS as a lab in orbit, and that is true, but it is also something else. It is the first rough prototype of a Starship ecosystem. One of the most important milestones there was the jump in water recovery. NASA said the station's life support system demonstrated the ability to recover about 98% of the water the crew starts with, up from roughly 93% to 94% before improvements to the brine processing system. That may sound like a technical detail, but it is not a small detail. That is a major step toward keeping people alive without constant replacement from Earth. And that changes the entire meaning of the spacecraft. Once you are talking about journeys far beyond Earth, water is not just a resource. It is a loop. Air is a loop. Waste is part of a loop. Heat is part of a loop. The spacecraft has to keep taking what people use up, cleaning it, recovering it, converting it, and feeding it back into the environment again. That is what makes the system Starship relevant. Not the fact that it flies, but the fact that it can keep a tiny human environment from collapsing in a place where there is no outside support. This is also where the glamorous version of space travel starts to fall apart. Real life support is not cinematic. It is pressure control, fire detection, oxygen generation, carbon dioxide removal, ventilation, humidity control, water processing, waste management, trace contaminant removal, and all the chemical and mechanical systems that connect those things together. NASA lays this out very clearly in its life support work. The system is not one machine. It is a whole stack of machines, sensors, filters, valves, processors, membranes, loops, and backups. None of that sounds exciting until you realize that if even a few of those parts fail in the wrong way, the mission can end without a single external impact or major accident. The crew can simply run out of a stable environment. That is why so many popular ideas about Starflight are incomplete. People obsess over the engine because the engine is dramatic. But if your life support stack cannot survive for years without resupply, then your propulsion breakthrough does not really matter. You can have a fast ship and still have no mission. If the atmosphere goes bad, if carbon dioxide starts building up, if water recovery fails, if waste handling fails, if contamination spreads, if a fire suppression system is not reliable, then the crew is in trouble long before distance becomes the main issue. And even with that ISS water milestone, it is still only one part of the problem. Water recovery is important, but it does not mean you have solved Earth independence. Food is much harder. Long-term nutrient cycling is harder. Waste reprocessing is harder. Growing food safely in a closed environment is harder. Managing microbes over long durations is harder. Keeping trace contaminants under control is harder. Air, water, and food are not three separate checkboxes. They interact. Once you move from short missions to very long missions, the spacecraft stops being a container and starts becoming something closer to a managed ecosystem. That is why the ISS should be understood correctly. It is not the finished answer. It is the beginning of the right kind of answer. It shows that closed-loop recovery can work better than it used to. It shows that human life support can become more regenerative and less dependent on constant shipment from Earth. But it does not mean we are ready to send a crew out for decades. It means we now have a crude early model of the kind of engineering that future deep space missions will need much more of. Then the problem gets even tougher, because the issue is not just closure. It is maintainable closure. A long-duration habitat does not only need systems that work, it needs systems that keep working, can be repaired, can be diagnosed, can fail without killing the mission, and can keep operating when spare parts are limited and outside help is useless. Filters clog, pumps fail, membranes degrade, electronics drift, seals wear out, sensors go bad, crew members get sick. Small faults become bigger faults. On a short mission, you can sometimes survive by carrying margin and waiting it out. On a mission leaving the solar system, you're building a machine that has to survive its own aging. That is where reliability stops being an engineering detail and becomes the mission itself. A true starship has to keep its own environment stable, while its parts slowly wear down over years or longer. That means redundancy matters, repairability matters, diagnostic intelligence matters, fault tolerance matters. It also means the crew cannot just be passengers. They are maintenance staff, emergency response, medical support, and systems management all at once. The ship is not merely carrying life. It is continuously producing the conditions that make life possible, and the crew is part of that production system. This is why the first human mission beyond the solar system may depend more on biology support than on propulsion. That sounds backwards at first, because people assume the engine is always the hardest part, but the engine may only be the ticket. The real barrier may be building a habitat that can keep humans healthy and operational for longer than any human vehicle ever has. Fast rocket does not solve that. Brave crew does not solve that. A historic launch does not solve that. You only really leave the solar system when your spacecraft can do something no human spacecraft has ever fully done before. Act like a stable, repairable, self-sustaining environment for a very long time. And that should make the whole story feel more serious. Because now the mission is not just, can we go far? It is, can we build a machine that can replace enough of Earth to keep humans alive when Earth is no longer functionally part of the mission? That is a much harder question. It is not just about reaching deep space. It is about surviving there without your environment collapsing around you. And then the next problem appears immediately. Even if you build that closed-loop world, it still does not live in isolation. It has to communicate, decide, and operate across distances where Earth stops being real-time support. So now the mission gets another layer harder, because distance does not only threaten travel and life support. Distance starts breaking command, control, and even the idea that Earth is still in charge. So what happens when the ship is healthy, the crew is alive, and the mission is still too far away for Earth to help in real time? That is the next break in the story. Distance does not only make travel harder, it changes command itself. It changes who makes decisions, how mistakes are handled, how information moves, and eventually what kind of human group the crew becomes. Once you go far enough, the problem is no longer just how to reach deep space. The problem is that deep space starts cutting Earth out of the loop. That is already true even inside the solar system. NASA's Deep Space Network exists because communication in space is not simple. It is not just sending a message and waiting for a reply. It is a full infrastructure problem. You need giant antennas, scheduling, precise pointing, signal recovery, error correction, power management, and time. Even now, spacecraft communication competes for limited network resources. That alone tells you something important. Space exploration is not only a propulsion problem, it is also a communications architecture problem. The farther you go, the more things like bandwidth, delay, antenna access, and signal quality stop being technical details and start defining what the mission can even do. And deep space is already difficult before you get anywhere near another star. Once you start talking about true interstellar distance, the whole situation changes again. This is where better communications help, but only up to a point. NASA's optical communication work has shown major gains in data rate compared with standard radio systems. That matters because it means future missions may be able to send much more information across deep space. Better imagery, better diagnostics, more science, more software support, more detailed updates. All of that is real progress, but none of that touches the deeper problem, which is delay. More bandwidth is not the same as less time. You can improve the pipe. You cannot remove the light travel limit. If the target is Alpha Centauri, a signal still takes more than 4 years to go one way. That means a message sent from Earth is already old by the time it arrives. A reply is older still when it comes back. At that point, communication is no longer conversation in any normal sense. It becomes historical exchange. Earth can send advice. Earth cannot control the mission moment by moment. Earth cannot talk a crew through an emergency. Earth cannot act like mission control in the way people are used to imagining. That is why autonomy is not just a nice extra for deep missions, it becomes the default condition. NASA already uses language like Earth-independent operations when talking about future human exploration, and that phrase is more important than it sounds. It means the crew and the onboard systems have to function without depending on fast support from the ground. Once command delay becomes too large, Earth stops being operational control and becomes something closer to distant oversight. The ship has to diagnose itself. The software has to manage routine and abnormal conditions. The crew has to solve emergencies locally. The mission stops being remotely piloted and starts becoming self-governing. That is a much bigger shift than most people realize. People still picture exploration using the old model. Crew goes out, mission control watches everything. Experts on Earth handle the hard decisions. The ship reports in, instructions go back, and the system works because Earth is still the brain. That model starts breaking even for deep solar system missions. For interstellar missions, it is gone. Not weakened, gone. Once the delay is measured in years, the ship, its automation and its crew become the real operational center, whether anyone likes it or not. And that means the spacecraft stops being only an engineering system. It becomes a local human system. It becomes a social system. Someone on board has authority. Someone decides what risks are acceptable. Someone sets rules for emergencies, resources, discipline, conflict, medicine, repair priorities, and maybe even long-term population management if the mission lasts long enough. These are not side issues. They are what happens when the old command chain can no longer function at mission timescale. Then the emotional side becomes just as serious. A 4-year one-way delay changes more than logistics. It changes what relationships even mean. Think about what that does to a crew member's connection with Earth. A message about a crisis goes out, and before any answer can come back, the crisis may already be solved, or the system may already be lost, or the crew member who sent the message may already be dead. News from Earth arrives as history, not as shared present time. Families do not age with you in real time. They appear in jumps. Institutions change. Priorities on Earth change. The world you left does not stay still while you travel, and you do not stay synchronized with it. That is why interstellar departure is not just deeper spaceflight, it is delayed civilization. Human beings evolved inside communities where conversation, reaction, and shared time were immediate or close to it. Even today, most social life depends on short feedback loops, but on a mission this far out, causality itself becomes part of the design problem. The crew lives in one-time reality, Earth lives in another. Neither side can fully participate in the other's present. That changes trust, authority, identity, and decision-making in ways that normal mission planning barely has to confront. And that is where the stakes rise beyond engineering. A crew prepared for true solar system departure may need more local authority than any exploration crew in history. More legal independence, more medical independence, more technical independence, more cultural independence too. Because the farther they go, the less practical it is to behave like a temporary expedition still fully anchored to home. At some point, they stop being a team on assignment and start becoming a small branch of humanity living under different conditions and different time rules. That sounds abstract until you think about the long-term implications. What customs survive, what language changes, what traditions still matter, what laws stay binding when enforcement from Earth is meaningless in real time. What happens if mission survival requires decisions that Earth would not approve of, but Earth's approval arrives years too late to matter? These are not science fiction side plots. They are what fall out naturally once communication to delay becomes large enough. The mission becomes culturally local whether it wanted to or not. So the question, when will humans leave the solar system, starts quietly changing shape again. It is no longer only about engines, radiation, or life support. It becomes a question about readiness for human communities that no longer live inside Earth's time, not just far away from Earth, but functionally out of sync with it. That is a very different threshold. It means the first true departures may require not only better hardware, but different ideas of governance, duty, identity, and control. And once you see that clearly, the next problem becomes even harder. Because even if you accept autonomy, delay, and cultural separation, there is still a final practical question waiting. Where are these people actually going? Because the nearest stars are still extremely far. The most interesting worlds may be hostile, and the best-looking destinations may be far beyond the reach of any first mission. So after all of that, there is still one question that sounds simple and turns out to be brutal. Where do you even go? People talk about leaving the solar system as if the hard part is the engine, and then after that you just pick a destination. That is not how this works. The destination problem is cruel because the nearest targets are still extremely hard, and the most exciting targets are usually much farther away. So even after propulsion, radiation, life support, and autonomy, you still run into another wall. The map itself is unfriendly. Start with the obvious target. Alpha Centauri is the nearest star system outside our own, just over 4 light-years away. That is why it shows up in almost every serious conversation about interstellar travel. If humanity ever sends anything big beyond the solar system, this is the first place people think about. And that makes sense. If you are going to attempt something this difficult, you start with the least impossible option. But that is the key phrase. Least impossible. Not easy. Not reachable in any ordinary sense. Just less bad than the others. That distinction matters because people hear nearest star system and mentally shrink the problem. They think nearest means maybe manageable with future technology. But Alpha Centauri is still far enough away that every current human mission starts looking primitive by comparison. You're not just dealing with travel time. You're dealing with braking. You're dealing with communication delay. You're dealing with autonomy that has to work for years or decades. You're dealing with a mission so stretched out that the world which launched it may not look the same by the time it gets close. So yes, Alpha Centauri is the first serious target. It is also the point where interstellar travel stops sounding like a bigger Mars mission and starts sounding like a completely different category of human activity. Then you get to the most tempting target in that neighbourhood, Proxima b. It gets attention for a good reason. It is roughly Earth mass, it sits around the nearest star to the Sun, and on paper it looks like exactly the kind of world that makes people think maybe, one day, there is somewhere for humans to aim. But the closer you look, the less comfortable it becomes. Proxima Centauri is a red dwarf. That means the planet is close to its star. Extremely close compared with Earth and the Sun. It circles in just over 11 days, and that creates a whole chain of problems. Now the target is not just far away, it is uncertain in the worst possible way. Is the atmosphere still there? Did stellar activity strip it away long ago? Is the surface being hit by powerful flares? Does the planet have magnetic protection? Is it tidally locked, with one side always facing the star and the other in permanent darkness? Could any atmosphere or ocean system stay stable under those conditions? This is what makes Proxima b so important and so difficult. It is not a second Earth waiting nearby. It is a scientific question wrapped inside a travel problem. Even the best nearby terrestrial-looking world might still turn out to be a very bad place for human beings. And then the next surprise hits. The galaxy is not short on planets. In fact, one of the most important changes in astronomy over the last few decades is that planets turned out to be everywhere. Thousands of exoplanets are already confirmed, and systems like TRAPPIST-1 make that abundance impossible to ignore. TRAPPIST-1 alone has 7 Earth-sized planets, which is extraordinary. On paper, that sounds like good news. It sounds like the universe is giving us options, but it does not solve the main problem. It almost makes it worse, because abundance is not the same as accessibility. TRAPPIST-1 is about 40 light years away, and that is where your intuition has to stay disciplined. 40 light years is not just a farther version of 4. It is the difference between a mission that some future civilization might at least discuss seriously, and a mission that may stay beyond practical reach for much longer. The existence of many worlds does not shorten the distance to them. Exoplanet science has shown us that targets are common. It has not shown us that targets are easy. That is one of the cruelest parts of the whole story. We now know the galaxy is full of possible destinations, but that knowledge does not make the first mission easier. It only makes the contrast sharper. The universe may be rich in worlds, but the routes to those worlds are still punishing. So the emotional effect is strange. Every new exoplanet discovery expands the future and tightens the present at the same time. You get more reasons to care, but not many new reasons to believe we can get there soon. Then there is one of the few shortcuts in this entire discussion. Before we reach another star, material from other star systems may keep reaching us. Interstellar objects passing through the solar system matter much more than they first seem to. They are not destinations in the normal sense, but they are pieces of other systems crossing our neighbourhood. That makes them incredibly important. Instead of sending a mission across light years, you wait for interstellar material to come through the inner solar system and try to intercept it. That changes the logic in a very interesting way. Suddenly, interstellar science does not have to begin with a full interstellar mission. It can begin with fast response missions inside our own solar system. Study the object, sample it if possible, analyze its composition, structure, maybe even its isotopic history, and now you are doing interstellar science without having to cross interstellar distance first. That is a real strategic shortcut. It does not solve the human travel problem, but it may become one of the first practical ways humanity studies matter from beyond our own stellar system in a direct and meaningful way. And this leads to the hardest point in the section. The first human target beyond the solar system may not be the world we most want. It may not be the most beautiful planet. It may not be the most Earth-like candidate. It may not even be a planet at all. The first target may be chosen because it is the least impossible one, because it is reachable with available propulsion, because it allows some braking option, because it offers high scientific value for lower mission risk, because it proves something important even if nobody can land anywhere. That means the first true human departure may not be built around arrival in the way people usually imagine. It may be built around crossing a threshold alive. It may be built around getting beyond the sun's final grip with a crew still functioning on board. It may be built around intercepting an interstellar object or entering a region of space rather than landing on a perfect world. That sounds less grand than the usual picture, but it may be much closer to reality. The early history of real exploration is usually not shaped by ideal destinations. It is shaped by what can actually be reached. So the destination problem does something very important to the whole story. It strips away the fantasy that the future mission will naturally go to the best available world. More likely, it will go to the best compromise, the best balance between distance, mission duration, risk, deceleration, science value, and survivability. That is a much harsher logic, but it is the one real mission planners would have to live with. And once you accept that, the next problem becomes even stranger. If the first mission may not be fast enough for a normal crewed journey, and the first destination may not justify a giant active population on board the whole time, then maybe the real decision is not just where the ship goes. Maybe the real decision is what kind of ship it is, and what kind of human life it carries while it is going there. So what if the destination is possible in theory, but the people on board cannot live through the trip in any normal way? then the biggest design choice is no longer the engine, it is the ship architecture. What kind of mission are you actually building? Because a normal crewed mission profile does not scale to interstellar distance. Take the kind of habitat people discuss for a Mars transfer and stretch it from months into decades. Almost every problem gets worse at the same time. You need more consumables, more medical capacity, more radiation protection, more exercise support, more maintenance, more spare parts, more autonomy, more social stability, more redundancy, and much more mass. At some point you stop extending a mission and start creating a completely different kind of human system. That is the hard fork in the road. Either the crew stays active for the whole journey, which means the ship has to function like a small society for a very long time, or you try to reduce the human burden during transit as much as possible. There is no hidden easy option between those two. If people stay awake and fully active, you need a much larger life support structure and much more onboard governance. If people do not stay fully active, then you need a medical and automation system capable of carrying them safely through a very unnatural state for a very long time. In both cases, the architecture changes the whole mission. This is why torpor keeps showing up in serious discussions. Not because it is science fiction, and not because it is ready, but because it attacks the problem in a way ordinary mission design cannot. NASA-backed torpor studies are some of the clearest examples of this. The idea is not full cryo-sleep in the movie sense. The idea is more like a reduced metabolism state inspired by hibernation biology, where the crew's needs during transit could be cut dramatically. NASA-supported work has looked at this seriously enough to study body temperature, oxygen consumption, ventilation, heart rate, and the way reduced metabolic states might interact with microgravity. That tells you something important. This is not a solved system, but it is not a joke either. That nuance matters. People hear words like hibernation or suspended animation and immediately jump to fantasy. But the real discussion is more technical and more limited. Full cryopreservation and perfect revival are still far away. That part is not ready. What is being studied is whether some form of torpor or long-duration metabolic reduction could become useful for future spaceflight. And if it could, the payoff would be enormous. Because torpor does not just help one part of the mission, it hits the entire mass and logistics problem at once. That is why this idea survives. In NASA-supported torpor studies, the possible reductions were not minor. Habitat mass and volume could fall dramatically compared with more conventional crewed transit designs. That matters because smaller habitat volume means less structure, less atmosphere to manage, fewer active crew needs, fewer day-to-day resource demands, and potentially a much simpler overall transit architecture. Once you reduce the metabolic and operational burden of the crew, you are no longer just saving food or water. You're changing the size and complexity of the entire mission stack. And that is exactly why torpor is so attractive for very long missions. It reduces life support load. It reduces consumables. It may reduce psychological strain because the crew is not consciously living through every day of the transit. It may reduce mission mass. It may reduce the scale of onboard habitat required during the crossing. If it works, it does not merely improve the mission, it redesigns it. That is the kind of leverage people are looking for when the distances get too large for ordinary human operations, but then the fine print arrives again, and the fine print is severe. Torpor does not erase the mission problem, it compresses it into a different form. Now your whole mission depends on precision medicine, continuous monitoring, fluid support, thermal control, careful cycling, and automation that cannot be allowed to fail. You're no longer building a ship for active people living normally on board. You're building a highly managed medical environment that has to sustain people safely through a state we still do not fully understand at long durations in space. That is not a smaller challenge. It is a different challenge. And the open questions are serious. How long can torpor safely last? How often does the crew need to be cycled out of it? What happens to bone, muscle, circulation, immunity, and brain function over very long durations? What level of medical intervention is needed during transit? How much automation can be trusted? What happens if the system partially fails halfway through the journey? What happens if one crew member wakes into a malfunction and has to manage the ship alone? The more seriously you take torpor, the more you realize it is not a cheat code. It is a trade. You're trading one kind of difficult starship for another. And that brings back the option many people do not want to think about. If propulsion stays too slow and torpor never becomes reliable enough, then the old fallback returns. The generation ship. This is the architecture no one likes because it forces the most uncomfortable version of the story. A generation ship is not really a mission vehicle in the usual sense. It is a settlement in motion. The people who arrive are not the people who launched. They are their descendants. At that point, the challenge stops being only engineering and becomes social design at the deepest level. Now the ship has to support not just survival, but a functioning human community over generations. That means law, education, healthcare, conflict management, identity, legitimacy, and long-term social continuity all become mission critical. Who has authority? What counts as consent for a journey no one on board originally chose? How do you educate children for a destination they have never seen and may never reach? How do you prevent social breakdown or simple loss of mission purpose over time? These are not side questions. They become the architecture. This is where the story gets much darker. If humans leave the solar system before we solve high-speed propulsion or reliable long-term stasis, they may not leave as explorers in the usual sense. They may leave as a population. They may leave as people born into transit, people whose home is the ship, whose culture was formed in confinement, and whose connection to Earth is historical rather than personal. That is a very different image from the one most people have when they hear the phrase first human mission beyond the solar system. And that is why ship architecture may decide everything, not just how the mission works, but what kind of human event it actually is. A fast ship with a small active crew is one future. A torpor-based ship with heavy medical automation is another. A multi-generational settlement is another. And those futures are not just different technical options, they produce different societies, different risks, different ethics, and different definitions of what it even means for humans to leave home. So the question keeps getting more serious. First, it was about the edge of the solar system. Then it was about propulsion, then biology, then life support, then communication and culture. Now it becomes a design question at the level of civilization. What kind of vessel can actually carry human life across timescales and distances this extreme, and what kind of humans would exist inside it by the time the journey mattered? And once you ask that honestly, the next step becomes obvious. Before any human mission like this happens, something else almost certainly goes first. Not because humans are unimportant, but because the risks are too large, the unknowns are too many, and the only realistic path forward is to send other systems ahead to test the route. So if human missions are this hard, what actually happens first? Almost certainly not humans. The roadmap runs through precursor missions, and that is not a sign of weakness. It is the only serious way this story moves forward. Before people go, the unknowns have to shrink. The technology has to harden, the distances have to become less abstract, and that means the real path to leaving the solar system starts with missions that test pieces of the problem long before they test the whole thing. That is why lunar and deep space missions matter more than they first seem. Not because the moon is somehow close to interstellar space. It is not. But because missions beyond low Earth orbit begin rebuilding capabilities that human spaceflight has not had to sustain for a long time. Radiation exposure outside Earth's protective environment matters. Greater autonomy matters. Reduced dependence on constant real-time support matters. Artemis-era missions are important in that sense, because they are collecting real data and rebuilding operational experience. Artemis 1 flew with thousands of passive sensors and dozens of active radiation detectors inside Orion. Artemis 2 planning includes radiation monitoring for the astronauts themselves. That may sound incremental, but this is exactly the kind of groundwork without which all interstellar discussion turns into empty talk. That is the first step in the roadmap. You do not jump from low Earth orbit to the stars. You rebuild deep space human capability one layer at a time. You gather radiation data, you refine shielding, you study medical response, you improve Earth-independent operations, you learn what happens when people and systems spend more time farther from home. The moon is not the destination in this story, it is part of the proving ground. Then come the robotic pathfinders, and this is where the outer edge starts becoming a real mission category, instead of a vague future idea. One of the strongest serious concepts here is the modern interstellar probe class. This is not a starship. It is not interstellar travel in the dramatic sense, but it is exactly the kind of mission that changes what humanity knows before any human departure is even worth discussing. Pragmatic probe using today's technology, built for a mission lifetime of decades and intended to return useful science from around 1,000 astronomical units, would completely change our understanding of the outer heliosphere and the local interstellar medium. That matters because right now the very far outer solar system still feels more theoretical than mapped. We know a lot more than we once did, but not enough to treat it like familiar territory. A serious long-duration interstellar probe would push that boundary outward in a way no current human mission can. It would not carry people, but it would do something almost as important. It would turn the edge from an abstract distance into a measured environment. It would tell us more about particle conditions, magnetic structure, dust, plasma, and the actual transition between the solar domain and the wider galactic environment. That is exactly the kind of knowledge a civilization needs before it sends human beings any deeper. Then there is an even more important milestone that sits between the outer solar system and another star, the solar gravitational lens. This is one of the most powerful ideas in the whole roadmap. The basic point is that the sun's gravity can act like a lens, and the useful focal region begins at around 550 astronomical units. That is still far beyond anything any spacecraft has reached, but compared with another star, it is much closer. And if a mission could get there and operate properly, it could potentially use the sun itself to help image exoplanets at a level far beyond what we can do from Earth or near-Earth space. That changes the whole interstellar debate, because one of the biggest problems with a first human mission beyond the solar system is that right now it would leave with limited knowledge of the actual target worlds. But a robotic observatory at the solar gravitational lens could dramatically improve that. It could give us far better reconnaissance of exoplanets before anyone tries to go there. Surface clues, atmospheric clues, possibly far more detailed imaging than current astronomy can manage. In other words, before humans ever leave the solar system, we may be able to study future target worlds in far greater detail from inside our own system by sending robots to the right place. And that leads directly into the next layer of precursor missions. Faster robotic architectures are already being outlined for exactly this kind of role. Some beamed power concepts aim at speeds above 40 astronomical units per year, which would be enough to reach the solar gravitational lens region in under 15 years. That is a dramatic jump compared with current spacecraft. It is not mature hardware yet, and no serious person should pretend otherwise. But it shows something important. There is now a visible chain connecting present-day deep space engineering to future precursor missions that actually start changing what is possible. That is why this part of the roadmap is so important. It is not fantasy stacked on fantasy. It is stepwise escalation. First, better human missions beyond low Earth orbit. Then long-duration robotic probes to the outer heliosphere. Then perhaps fast precursor systems to major milestones like the solar gravitational lens. Then maybe laser sail scouts to nearby stars. Every step reduces ignorance and increases confidence. Every step pushes some part of the problem from unknown into measured reality. And this is the main logic that should now be unavoidable. Humans probably go last, not first. That is not pessimism. It is the structure of the problem itself. Before humans go, propulsion has to improve, radiation protection has to improve, closed-loop life support has to improve, long-duration habitat reliability has to improve, autonomous operations have to improve, governance for delayed missions has to improve, reconnaissance of target environments has to improve, There is no serious path where human beings skip over all of that and go first simply because the idea sounds historic. So the first real human departure from the solar system will probably not feel like the first step in the story. It will feel like the last confirmation that all the earlier steps worked. A late result, not an early one. Not the beginning of the roadmap, but the moment when every piece finally lines up enough to justify putting human lives on top of it. And that should make the final question unavoidable now. After all the definitions, all the propulsion limits, all the biological limits, all the habitat demands, all the communication delays, all the destination problems, and all the precursor steps, what is the actual answer? Not the dramatic answer, the evidence-based one. When will humans finally leave the solar system? So when will humans finally leave the solar system? After everything you have seen, the answer depends completely on which line you are calling the finish line. If the line is the heliopause, then the first part of the story is already over. Voyager 1 crossed into interstellar space in 2012. Voyager 2 followed in 2018. By that definition, human-made objects have already gone beyond the sun's plasma bubble and entered the space between stars. That is real. It happened. But it is also very easy to say more than that fact actually proves. Those were robotic victories, not human ones. And they do not prove we are close to sending people. They prove something narrower and still impressive. Hardware designed in the 1970s can cross one important boundary if you let it travel long enough. So if the question is just, have we begun leaving? The answer is yes. If the question is, are humans close behind? The answer changes fast. Because once you switch from a machine to a crew, every difficulty scales up at the same time. Radiation scales up, mass scales up, life support scales up, reliability scales up, time scales up. Autonomy scales up. The boundary that Voyager crossed is real, but it is not a shortcut around any of the human problems. It only proves the path exists in a physical sense. It does not prove we can survive it. So what if you mean a human crew crossing beyond the heliosphere? That is the version most people actually mean, and this is where the answer gets much less comfortable. Based on what is real now, not what people hope will appear, a human mission beyond the heliosphere this century looks unlikely. Not impossible in the strict sense, but unlikely. And the reason is not one missing piece. It is the pile-up of many unfinished pieces. Human spaceflight is still dealing with Mars-scale problems that are not fully solved. Radiation is still a mission-limiting issue. Bone and muscle loss are still serious. Artificial gravity is still not a standard capability. Closed-loop life support is improving but nowhere near full Earth independence. High-power propulsion for human deep space travel is still at the stage where even interplanetary use is the main target. That is the important point. The technologies people mention as the next big step are still aimed mostly at Mars-class or deep solar system missions. Nuclear thermal propulsion could help a lot, but it is still a bridge technology, not an interstellar one. High-power electric propulsion could help a lot, but it is still being shaped around mission profiles vastly smaller than a human heliopause crossing expedition. Even the most promising upgrades we talk about today mostly make hard solar system missions more manageable. They do not yet make human departure from the heliosphere look like a natural next move. And that means the timeline people casually imagine is almost certainly too aggressive. To get a crew beyond the heliosphere this century, you would need multiple major advances to arrive together, not one after another over a long period. You would need stronger propulsion, better shielding, much more reliable closed-loop habitats, stronger medical countermeasures, far more autonomy and mission architectures that can stay stable for a very long time. That is a very high bar. Could it happen if several breakthroughs hit at once? In principle, yes. Is that the evidence-based expectation right now? No. Then the question gets even harsher if you use the stricter meaning of leaving the solar system. What if you do not mean the heliosphere at all? What if you mean leaving the sun's deeper gravitational domain in the Oort Cloud sense? Then the answer moves even farther out. Because now the target is not just beyond the plasma bubble, it is thousands to tens of thousands of astronomical units away. And that scale is so much larger that even the most exciting precursor concepts people discuss now still look like early robotic groundwork, not human departure. A robotic precursor moving at over 40 astronomical units per year sounds incredible, and for robotics it is incredible. A mission reaching the solar gravitational lens region in under 15 years would be one of the biggest deep space achievements in history. But even that is still nowhere near the full outer Oort Cloud scale, and it says nothing by itself about keeping people alive on board. That is the correction people usually do not make. They hear a fast robotic concept and mentally slide from good for probes to maybe workable for crews. That slide is not justified. Human payloads are not just larger versions of robotic payloads. They are fundamentally harder. So if finally leave the solar system means beyond the sun's deeper outer gravitational reach, then the realistic answer is probably not this century. It is more likely a 22nd century project, and a 23rd century timeline may be more realistic if progress continues in the step-by-step way it usually does instead of exploding forward through multiple major breakthroughs at once. That answer sounds slow only because the question sounds simple. Once you define the target honestly, the timeline stretches with it. Then you can narrow the futures down to something more concrete. There are probably two broad ways humans get out. In the first future, propulsion improves but not enough to make the trip short. That means humans leave slowly, in very large habitats, or in torpor-based systems, or in some kind of generation-style architecture where the mission is designed around long duration from the start. In the second future, propulsion jumps much harder, maybe through mature beamed systems, maybe fusion, maybe something else with much higher delta V than anything operational today. In that future, smaller crews might cross outward on timescales of decades rather than centuries. Right now, neither future exists in operational form, and that is why the answer has to stay disciplined. The slow future depends on solving the body problem and the closed-loop ecosystem problem. The fast future depends on solving the power problem and the propulsion problem. At the moment, both futures are still mostly conceptual beyond the near solar system scale. We can see pieces of each one. We cannot yet build either one all the way through. So the best evidence-based answer is this. Robots have already begun leaving. Better robotic precursor missions pushing much deeper toward the edge of the heliosphere and beyond may become plausible in the late 21st century or early 22nd century. But the first human beings to truly leave the solar system in a scientifically serious sense are more likely a 22nd century outcome at the earliest. And if progress in propulsion, radiation protection, artificial gravity and closed-loop habitats continues at the kind of pace we usually see in hard engineering, then a 23rd century outcome may be more realistic. That is not pessimism. It is just what the numbers look like when you stop confusing farther than ever with finally free. Humanity is getting better at going farther. That is true, but going farther is not the same thing as leaving. Crossing the heliopause with a probe is not the same thing as taking a crew beyond the sun's lasting reach. A fast Mars architecture is not the same thing as a solar system departure system. And a serious answer has to keep those differences intact. So yes, humans will probably leave the solar system one day. But if you are asking for the honest answer, not the exciting one, then the honest answer is that the first real human departure is probably not near. It is later than people want, later than headlines suggest, and later than most casual space discussions admit. The machines have started the process, the humans have not caught up yet. And that leads to the final point of the whole story, because once you have given the timeline answer honestly, one bigger truth is left standing. The real ending was never just about a date. It was about what kind of civilization would have to exist before that date could mean anything at all. So what is the real ending to all of this? It is not a launch date. It is not a rocket. It is not one heroic crew. The story starts with a definition, but it ends with a civilization. At the beginning, the question sounded like a countdown. When will humans finally leave the solar system? That makes it sound like all we are waiting for is one big mission. But the science keeps forcing the same answer from every direction. Leaving the solar system is not one milestone. It is the point where propulsion, radiation protection, autonomy, life support medicine, and long-term social stability all become good enough at the same time. If even one of those fails, the mission fails with it. That is why the real subject here was never just one spacecraft. It was whether Earth can build a second Earth in motion. Not another planet and not a perfect copy, but a moving system that can keep human beings alive and functioning without depending on the world that launched them. That is the real threshold. Not crossing a line on a map, but carrying the conditions of survival with you so completely that deep space stops being a place that kills you by default. Voyager showed us the first piece of that future, and it did it in the most uncomfortable way possible. 2 probes launched in 1977 have already gone beyond the heliosphere. They are still moving outward at a few astronomical units per year. They have lasted for nearly half a century. They proved the wall around the solar system is not sealed shut. Human-made technology can get through it. That matters. But Voyager also proved something harder. It proved that machine reach and human reach are not even close to the same thing. A probe can cross a meaningful boundary long before a human mission can survive the same path. That gap is where the next centuries of space history will happen. Machines will go first, farther, faster, and in larger numbers. They will map, they will measure, they will test routes, they will test communications, power systems, autonomy, propulsion, and survival strategies. And all of that is necessary because human departure is not just a scaled-up version of a probe mission. A probe can fail slowly and still teach you something. A human mission cannot be designed that way. A probe can live on tiny power and limited hardware. A human mission has to protect biology every minute. A probe can drift through interstellar space. A human mission has to carry an environment. That is why the first real human departure may not look victorious in the usual sense. It may look fragile. It may look cautious. It may be a very small crew in torpor, kept alive by systems that have to work for years without major failure. It may be a huge rotating habitat that feels more like a closed settlement than a ship. It may be a mission whose only symbolic goal is to get a living crew beyond the heliosphere and prove human survival at that distance before anyone even talks seriously about another star. Or it may happen much later, after robotic scouts and solar gravitational lens observatories have already studied future target systems in extraordinary detail. However it happens, it probably will not feel like conquest. It will feel like trust. Extreme trust. Trust in reactors, recyclers, shielding, medicine, software, structure, governance, and systems maintenance. Trust in a machine that has to keep producing the conditions of life in a place that offers none for free. And that is why the usual version of this story is so misleading. People think the barrier is that the universe is big. The universe is big, but that is not the deepest barrier. The deeper barrier is that human beings are still built for a very specific world. We are built for gravity. We are built for air. We are built for a magnetic shield we did not construct. We are built for a biosphere we did not have to maintain ourselves. We are built for repair chains, hospitals, farms, weather systems, and real-time conversation with other people. Everything about ordinary human life assumes that the environment is doing most of the support work in the background. Deep space gives you none of that. So the moment humans finally leave the solar system, the biggest change will not just be in the spacecraft. The biggest change will be in us. We will have become a species that can build and trust a complete survival system away from Earth. That is a much bigger change than faster rockets. It means trusting machines for longer than any human culture has ever trusted them before. It means accepting delayed contact, local governance, and environments that are maintained rather than given. It means designing not just vehicles, but functioning human worlds that can stay stable in transit. In that sense, the first true departure from the solar system will say less about how bold we became and more about how technically mature we became. That is also why the final answer should stay very clear. The ending is not someday soon. The ending is not as soon as we build a better engine. The ending is not even when we reach interstellar space, because machines have already done that. The real ending is this. Humans will finally leave the solar system when we stop treating deep space as a destination and start treating it as an environment we can survive inside. That is the standard. Not distance alone. Survival, continuity, reliability, a human community that can keep going without Earth doing the hidden work underneath it. The probes have already shown the direction. Physics has shown the cost. Biology has shown the weakness. Engineering has shown the missing pieces. The roadmap has shown the order. What is left is time, and probably a level of technological maturity that does not belong to this moment. So the final answer is not a countdown. It is a condition. Humans leave the solar system when Earth becomes capable of building a second Earth in motion, small enough to fly, strong enough to endure, and stable enough to keep human life going in the dark long after home is too far away to help. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.